Welcome to part 1 of the divergence theorem. The goal of this video is to determine the flux of a vector field in space. The divergence theorem states the total divergence of a vector field in a solid region V equals the total flow across the boundary surface S. And here are the conditions. V must be a solid region bounded by S oriented by a normal unit vector directed outward, and the partial derivatives must be continuous. The divergence theorem states the double integral over the surface S of f dotted with n ds is equal to the triple integral over the solid V of div f dv, where div f, or divergence of f, is equal to the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z, where f, g, and h are the components of our vector field f. So this theorem shows the relationship between a triple integral over a solid region and the surface integral over a surface. And this theorem is a three-dimensional version of the flux form of Green's theorem discussed earlier. Let's take a look at our first example. Here we want to determine the flux of the given vector field across the surface x equals 0, x equals 2, y equals 0, y equals 2, z equals 0, and z equals 4. So these 6 planes would form a box. Let's go and take a look at this graphically. So the 6 yellow planes represent our surface. You can see they do form the boundaries of a solid as well. And in purple we have our vector field. So using the divergence theorem, we can determine the total divergence of the vector field in this solid region, which is also equal to the net flow across the entire surface. Let's go ahead and solve this problem. So our flux is going to be equal to the triple integral over the solid region V of div f times dv. Well, div f is going to be the partial derivative of f with respect to x, that's going to be 2x, plus the partial derivative of g with respect to y, that's going to be 2y, plus the partial derivative of h with respect to z will be 3z squared. And based upon our solid, the order of integration really doesn't matter. Let's go ahead and integrate with respect to x, y, and then z. The limits integration for x will be from 0 to 2. The limits integration for y will be from 0 to 2 as well. And then for z, it'll be from 0 to 4. So this is pretty straightforward. Integrating with respect to x, here we're going to have x squared plus 2xy plus 3xz squared. Keep in mind here we're only replacing x with 2 and then with 0. So we're going to have 4 plus 4y plus, here we'll have 6z squared. Integrating with respect to y is going to give us 4y plus 4 times y squared over 2, that'll be 2y squared. Here we'll have plus 6yz squared. And now we're going to replace y with 2 and then y with 0. So when y is equal to 2, we'll have 8 plus 8 plus 12z squared. That's going to give us 16 plus 12z squared. plus 12 times z cubed over 3, that'll be 4z cubed. So when z is equal to 4, we'll have 16 times 4, that's 64, plus 4 times 4 to the third, that'll give us 256. And then when z is 0, they're both 0. This works out to 320. So since our unit normal vectors are pointing outward, and this is a positive value, this tells us our flow rate out of the box. Now, even though all of these vectors appear like they're pointing upward, the vectors toward the bottom that are pointing in toward the box are much shorter, and therefore the net result is an outward flow from the box. We're going to stop here for part 1. We'll take a look at a second example in part 2. Thank you for watching.